August 24, 2001. An Airbus A330 carrying 306 people is flying at 39,000 feet over the pitch-black Atlantic Ocean. Everything is entirely routine. Then, the right engine abruptly shuts down. The flight crew is still trying to diagnose the issue when, exactly 13 minutes later, the left engine goes quiet. Instantly, the aircraft loses all main electrical power. The complex digital arrays in the cockpit go completely dark, plunging the cabin into silence. The massive aircraft is now an unpowered glider. Commercial pilots train for countless catastrophic scenarios, but a total dual-engine failure caused by a mid-flight fuel leak was not one of them. There was no recorded case in commercial history, and no checklist to tell the crew what to do next. To understand how a modern engineering marvel simply runs out of fuel miles above the ocean, we have to pause this descent and rewind. The cause of this crisis tracks back to a chain of microscopic, compounding errors on the ground. The timeline starts 9 days earlier, on August 15th. The airline's maintenance team needed to replace the plane's right engine, but they only had an older Rolls-Royce model available on loan. Working under a tight Sunday afternoon deadline, the mechanics ran into a problem. The plane's new hydraulic pump didn't fit properly onto the older engine. The manufacturer's service bulletin explaining the fix was available on a CD, but the local network was down. Without access to those instructions, the lead technician took an took-group shortcut. He forced a newer design fuel tube onto the engine, alongside an older design hydraulic tube. The manufacturer strictly warned that these two specific parts should never be installed together. Once the plane was in the air, the extreme pressure and vibration of flight caused those two mismatched metal tubes to rotate and violently rub against one another. Over several flights, the friction carved an L-shaped crack directly into the wall of the fuel tube. By the time Flight 236 was over the Atlantic, that tiny fracture was allowing fuel to hemorrhage from the aircraft at a rate of 13 metric tons per hour. A millimeter-level discrepancy in metal piping, installed under the pressure of a rushed schedule, created a mechanical time bomb. Even with a massive leak, the pilots could have potentially intervened, but this specific model of the Airbus A330 lacked a direct automated sensor to warn the cockpit that fuel was actively escaping the aircraft. After nearly 5 hours in the air, the crew finally received a vague automated alert pointing out a fuel imbalance, meaning there was considerably less fuel on the right side of the plane than the left. This is where a cognitive error compounded the mechanical one. Instead of pulling the official emergency checklist, which specifically dictated how to handle a suspected leak, the crew relied entirely on their memory. They assumed it was a routine computer glitch and executed a standard fuel balancing procedure. To balance the tanks, the pilots opened what is known as the crossfeed valve. This is a system designed to pump fuel from a full wing tank across the aircraft into an empty wing tank. By opening that valve, the pilots were unknowingly draining their remaining good fuel out of the left wing, sending it straight through the L-shaped crack in the right wing and dumping it into the ocean. 4 years earlier, a French investigation into a near-identical leak strongly recommended that aviation authorities mandate automated warning systems for these precise situations. The industry had not implemented them. The total loss of power over the Atlantic was caused by a fractured pipe, but it was accelerated by missing digital safeguards and human overconfidence in the cockpit. Back in the dark cabin of Flight 236, the tanks are completely empty. With both engines dead, the crew is forced to attempt the longest powerless glide in the history of commercial aviation. Their only mechanical lifeline is the ram air turbine, or RAT. It's a small, wind-powered propeller that automatically deploys from the belly of the plane, spinning in the slipstream to generate just enough emergency power for bare minimum steering control. At the controls is Captain Robert Pichet. Pichet had a highly unorthodox background. He had spent years as an off-grid bush pilot, landing in remote environments, and had served time in prison for drug smuggling. That rugged experience instilled him with deeply instinctive flying skills that standard commercial training couldn't replicate. Relying on gravity and momentum, Pichet manually maneuvers the silent, heavy aircraft through the dark for 19 grueling minutes. They cover an agonizing 144 kilometers, aiming for a remote military runway in the Azores Islands. Without engine power to provide reverse thrust, they slam down onto the asphalt at high speed. The extreme braking blows out tires, sending sparks flying from the gear, but the massive plane finally stops. All 306 people survive. The terrifying incident highlighted a sharp paradox. Human rule breaking on the ground created the nightmare, but unconventional human skill in the air was the only thing capable of ending it. The airline was eventually hit with the largest fine in Canadian aviation history, and the passengers pursued a massive lawsuit over the severe psychological trauma of preparing to crash into the ocean. For engineers and operators, the flight remains a definitive case study. Catastrophic failures in complex systems rarely happen because of one sudden explosion. They happen when a slow alignment of offline manuals, skipped steps, missing warning sensors, and memory-based shortcuts stack up perfectly. The ultimate safety net standing between a routine operation and a desperate fight for survival is unwavering adherence to the tedious, boring rules we so often take for granted.